Okay, so this is video 2, lecture 2, and in this video we are going to again extend the definition of a simple learning model, the perceptron, which we started building in video 1. Okay, so here I'm going to write more formally what the input looks like. So if you remember from the previous video, our input is nothing but a feature vector. So each element or each component actually gives us some representation of a feature or an attribute of the customer, right? So this is a d-dimensional vector, and then we decided that each feature or each vector has some level of importance, and then we eventually came up with a score which is credit score. Let's call it credit score because this is the credit card application problem, so let's call it that. And we came up, and I'm summing those values up because if you remember what we had, like let me make a small box here for a reminder. We had something like this, right? X1, W1, X2, W2, and so on for whatever number of vectors we have, which is D in this case. So we need to have a summation starting from 1, right? So this is the first element, and go up to D, which determines the number of features we have for this particular customer or customers, and this, right? So this is my credit score. And then the rule that we came up with was that we are going to approve or deny, right? So I'm going to approve credit. Let me write it. I'm going to approve credit if this value, which is credit score, I equals 1 up to D, WIXI, is greater than some predetermined threshold. And this predetermined threshold again could be anything from our domain knowledge, basically determining whether credit score is good or bad, right? So if it's good, greater than good is everything is good, let's approve it. Decline it, right? So decline credit if the summation, which I'm calling my credit score, starting from 1 up to D, WIXI, is less than the threshold, right? So again, that's what we decided, right? So approve or decline depending on whatever the value of the credit score is. And if you remember, these W's that we came up with, these weights were essentially telling us how important that feature is, how important that particular, like for example, if this feature was salary, how important that salary is. Based on that, I'll decide the weight for the salary, right? So if the salary is important, I should have a large magnitude of the weight. And if it's less important, then I'll have a smaller value. And the way this, like each of these weights impacts the features, for example, if you remember, the second one was debt, and it inversely impacts my credit score, right? So larger the debt, bad it is for the score, right? Bad it is for approval, or if we give that person debt, right? Sorry, if we give the approve the application for that person, so that's not good, right? So this particular feature impacts my credit score negatively, right? So then that will determine the sign of these weights, right? So I can have a negative weight and a positive. It is if it is impacting the overall value in a positive manner, right? So that the values there, or like the signs, will determine that. Okay, so having said that, I have formally defined a rule which I can write it more concisely here. Here, which is I can combine both the approval and the decline of the application, right? So if we go back and check, like I can combine these two into like a single equation. So essentially what I'm trying to do is I'm trying to determine the sign, right? Let me write it down. Trying to determine the sign of this particular equation. Let me write it. I from 1 to D, WIXI minus threshold. If we rewrite both these equations together, right, bring threshold this side, then we are essentially trying to determine the sign of this particular expression, right? If the sign is positive, then I approve. If it is negative, then I decline, right? So this is writing it more concisely in a single line. I can write my rule of whether I want to accept the application or I want to decline it, right? Okay. Even better, we can write a more convenient notation for this, and then for this rule, which I will call my final hypothesis for this particular problem. But first, try to like think about it. So like I tried to determine these W's for some given input, which was nothing but the attribute of these features. And then I came up with this rule that I'm going to approve or decline based on the sign of this expression, right? So basically what I'm saying here is my g of x, if you remember, g is going to be my final hypothesis. So in this situation, my g of x, x is the input vector, right, is nothing but the sign of I equals, or this expression essentially, right? So I'm not going to write that, but what I'm going to do is like write a more convenient expression for this, like right hand side. Okay, what could be that? Well, can I get rid of this threshold? Well, one way of saying that is, can I like put this or incorporate this in this expression? Well, the answer, short answer to that question is yes. I can make it more generic in the sense that this threshold, sometimes also known as bias, can be represented by W0, although that W0 does not exist because features begin from 1, right, and then go up to D. But then let's assume that this feature W0 exists, which is nothing but this threshold, right? And if I want to add this threshold to this expression, I need to have an x, which obviously does not exist, but because we are trying to represent this threshold by something, so I can come up with an x0, which is always 1, right? So then you can see the w0, x0, and like a negative of this can be like incorporated in this expression. And then this expression, let me rewrite it, becomes something like this. So the only thing that changes here, right, is that the sign of I equals 0. Now focus on I equals 0 because until now the summation was from I equals 1, right? And goes until D and then Wi xi. It didn't really change anything much because this entire thing can be represented by this new variable, that's W0, and x0 will always be 1. Right, so this is more convenient because as you can see, this is compact, and this is my final hypothesis for this particular problem. Okay, a little bit more about the notation before we move on, right? So let's look at, like, analyze this particular expression, what's going on in here, the dimension of the dimensions of the w's and the x's. Now, if you remember when we started talking about the input, we said that this is a d-dimensional vector, which was true, right? But now we have like this additional term as a result of my threshold, right? So originally, and I'll come to the perceptron hypothesis set. So let's like think of it that I'm like building towards that, but I'm still not there yet before I describe this notation, right? So originally my x was a d-dimensional vector, right? But now I have this augmented value, which such that x has this like x0 and then x1 and so on up to xd, right? And this x0 I know will always be 1. Right? So another way of writing this x, right, would be that this x, maybe I can write here, or continue writing, like get rid of this. Instead, I can write this as 1 because I know this will always be 1. And so x as a result belongs to a set of like 1s times my d-dimensional space. Right? So this is like the new dimension of x. Similarly, for w, what I have is now I have this like w0, w1. Earlier, I did not have that, right? So w2 and so on up to wd. And so the dimension for w is rd plus 1. Right? So I've just like augmented it. And so this is known as the augmented value for x, right? So, or the dimension for x. And that's because we have that like 1 added value. And you know why that is added, because the whole idea of perceptron was based off of the fact that there's the threshold that exists, and we wanted to have a more generic formula, and we wanted to incorporate that in my w times x, right? Okay, and so finally we come back to what my g was, right? And this was my g in the sense that I decided based off of like whatever information I have of the problem that my g of x is essentially going to be sine, and to write it in a better vector notation, w transpose x, right? Because this is a dot product. Okay, so we want my final g to be as close to my target function as possible, right? But here I was sitting and thinking of these w values, right? I said, okay, salary is important, give it 6. Okay, debt is less important, give it 3, and so on, right? I came up with those values. Maybe I had some information, maybe I did not have, right? So my point is that these W's that I came up with may not be correct, right? And also, I don't know whether this represents my F or not, right? So these questions still remain, but what I can definitely say that, like, this edge of, like, this g of x, right, with all possible w's, can still be thought of representing that larger hypothesis set that can have infinitely like as many values as I can think of w's, right? So I can have like these infinite number of hypotheses that will represent my entire solution set from where my algorithm is going to pick up certain values. So that thing can be fixed, right? So my hypothesis set can be fixed here. So basically what I'm trying to say is that if I say that my hypothesis set H, right, is a set of all these values that are represented by this linear model, and notice like I'm replacing G with this H of X because this is like a more generic form of representing this by this sign of W transpose X, right? If I could replace that with this, right, and this definitely can have uncountably infinite H's, right? This entire hypothesis set, this thing here, is known as the perceptron, right? I agree that I picked up these values of W's. There was just like one specific set of values out of this, but this entire set can still be termed as like an entire candidate set of solutions for my problem, for my credit card problem. And so this is known as my perceptron. So if you think of that older picture, if you remember, I don't have enough space here. Let me quickly draw that here, right? So if you remember, like when the older picture where we had like the target function going into the data, right? This was the training data, and I'll talk about it later, why this is known as training data. And then this was going into an algorithm, right? And then finally to G, which has to be close to F, and a hypothesis set, right? So now for the perceptron, this is my hypothesis set that I just came up with, right? Now, what was the learning algorithm in this entire thing when I decided for the weights? Well, if you think about it, I was my learning algorithm because I just like picked up those weights based off of certain information that I had about it, and then said, okay, this W is should be this, W2 should be this, and so on, right? So I have definitely fixed my hypothesis set, which is this linear model. This is why this is linear, because this is linear in the variables, right? But my learning algorithm is still kind of an open like question, right? Because I was the learning algorithm. I just picked up like some weights there. So I need to replace myself with a certain logical set of steps, right, in order to pick the correct W's, right? I don't know whether these W's are correct or not and how close my final G is to F because this is my goal, right? So I don't know that, and for that reason, what we are going to do is we are going to learn in the next video what the perceptron learning algorithm does. What specifically that does, that is nothing but a sequence of steps that will lead us to some W, which I'm calling W star, which will make things better for us. Right, so I'll just like stop here for this section of this lecture and then see you in the next video. Thank you.